We are back once again. Welcome, my fellow homunculi. This is day 23 of the daily LeetCode grind. It is what it is. We're back. 1 hour and 30 minutes on the clock as usual. 20 minutes a problem. In fact, I've been looking at this grind 75 based off a tip from a local LeetCode grinder, the Control Copy Ninja, and it seems like too good of a resource not to use. So, wanted to go ahead and try that. Wanted to go ahead and try this. I think it's cooler to be able to see, like, okay, you do a problem, right? Let's say you're grinding LeetCode, you're grinding anything. You're kind of being tasked upon yourself to localize this knowledge somewhere in your head, right? Organize it. And the finding method of explaining things to people, usually helps with organizing information. But I think just having a further method of grouping them makes it even easier to localize this knowledge in your head. For example, after doing all these problems, I'm sure I'll have something in my head about, the general nature of array problems and messing around with arrays. But at the same time, want to attack the weakest spot. The weakest spot is where you end up gaining the most. So I don't know if we'll do every problem in this. Some of them I've already done, like majority element contains duplicate. Don't think I've ever done sort colors. I've done best time to buy and sell stock a long time ago. I don't remember how I did it. And we never did TwoSum. So maybe what we'll try is that now, since we're going to be starting from a new spot every time, or a new problem, I'm still going to work on the top 100 questions, but I think the grind 75 is a better way. Hopefully, we'll test it out to group the patterns in these problems. From there, I think we'll just kind of shotgun problems depending on problem lists outside of recording. I think it's kind of dilemma as well, because I record my practice here, but I think I also need a way to get practice outside. But at the same time, in terms of organizing practice, there's maintaining, right? And there's working on new problems. And working on new problems helps with exposure, but I think there also needs to be a method of exposure which is going to force one to generalize their information. For example, if someone builds a box using the same instructions the same way every single time, that can have its cons when you're forced to build a box a separate way, right? You might find that being exposed to different methods to build a box allows one to generalize the way that they build a box to more scenarios. Very bad example, but it is what it is. Basically, I need a method of automating exposure to newer problems. Even if I can't solve these problems, I think it just helps to loosen the mental models I'm using to calculate how to write the code for these problems. That being said, the grind 75 is just going to be the main Johnsky, and we'll sample exposure problems from the top 100 list. And there's overlap here, so in a way we're doing both, so I don't think it's a net loss or net gain. Just want to try this out and see how it works. But I do think I'm kind of haphazardly doing problems. I need a better way of organizing the progress. So I think if we can do this, then we'll have a better grasp on pretty much all of how these things can work. That being said, I kind of feel strong already on arrays, but I could be deceived. I haven't done many mediums in arrays, so we'll do maybe half in each week and see how we feel. So I think I'll start with best time to buy and sell stock. Actually, we'll probably start with trapping rainwater, since that's what we started with yesterday. So I want to finish on this problem, give this problem 20 minutes. And then we don't have any problems, any new cards due today, so that's fine. So we'll probably do trapping rainwater because that's what we did yesterday. And trapping rainwater is actually one of the hard problems on here at the end, I think. But we'll do it here. I feel much better about my solution to this problem. And I also think it's really important to find solutions that work with your basic like psychological profile. I find that a lot of the solutions that are more procedure oriented, like if I was given this task in real life, how would I solve it? I end up just writing the sequential series of those instructions as code. So situations that kind of code solutions that kind of border closer to visualizing the problem in real life and executing a set of series of instructions tend to fare better for me in terms of how I remember problems. So when I'm reading the solutions, I always try and look for a solution that fits closest to my psychological profile. And I feel like that's a good tip. So, gonna retry trapping rainwater. Feeling good about it. After that, we'll do a random weighted problem. Then after that, we'll do grind 75. And we'll just basically go half and half. New problem on grind 75. Random weighted problem, new problem, random weighted problem, so on and so forth. So I'm just gonna start the timer now. So we have both timers going and make sure I'm recording. Sounds coming through. Hat's looking kind of drippy. Hey, might be merch coming soon. Also, don't forget to join the Hyperbolic Coding Chamber Discord. There are thousands. We finally got email back from Discord. They're going to allow us to have a second Discord with a new increased cap of people. So they gave us 2 servers, but actually they wrote some custom code for us to tie them together. So that's pretty hype. Make sure to join the Discord. It's pretty epic. And yeah, we're just gonna jump into trapping brain water. So function trap, we have a height, and we're given an array of numbers, and we have to return a number. So given n non-negative integers representing an elevation map where the width of each bar is 1, compute how much water it could trap after raining. So we have this height array here, 0, 1, 0, 2. So we can see that the number represents a block, 0 represents no block. And we see that water exists when there exists a space between 2 blocks that can hold water. When the minimum height, the ending height of the... So I think we can see that water exists when if we have a block, if we can find another block for which the height of that block is greater than or equal to that starting block, then water exists. So 1 here, we can find another block which is greater than or equal to 1, so 1 block exists. And it seems the number of water blocks exists between the minimum height of the 2 blocks. So we have a block of 1 and a block of 2 here, and the water block that exists is 1. So we have another 2 here, and the highest block that we can find that's greater than or equal to 2 is here, which is 3. And so if we check this range, which would be 2 and 3, we can calculate 4 by saying that the minimum height is 2. We can do 2 minus 1, which is 1, 2 minus 0, which is 2, 2 minus 1 is 1, 2 minus 3 is not greater than 0. That would give us 4 blocks calculated. The problem with this solution is that it doesn't handle well when the premise is flipped. So the premise is that we start with a lower block and find a block that is greater than or equal to our minimum height, which means our left-hand side usually has to be the smallest one. In this case, where we have 3 right here, when we try to find a block that is greater than or equal to 3, we can't find one. But we know that water does actually exist, right? And so I think what this means is that we want to come at this from a 2-sided approach where we'll iterate from both ends of the array at the same time, and we'll try and choose the height that is smallest between the 2, right? So if we start at 0 and 1 here, right, 0 would be less than 1, right? But also it's not greater than 1, right? So we'd increment forward. Right. So let's try and I can't see. I shouldn't look. let's try and write the pseudocode for this. We want to iterate from both sides simultaneously. This will also allow us to not have to recalculate many things over and over and over again. So in a way, this saves us, this allows us to reuse our solution. So iterate from both sides will have a left and a right pointer, both starting at 0 and 1, right? But 0 is too low, right? So we want to make sure that wherever we're starting at, So where I'm stuck right now is that I actually I'm curious as to, usually when we're iterating from both sides, we need a step to increment, right close to the center and left close to the center. So I'm struggling as to where to place that. But I'm thinking in this original case, we'll find that height 0 is less than height 1, right? So we want to say height sub left is less than right, right? Then we kind of found our premise that we like, right? At 0 is less than 1, right? So we want to find one that's greater than or equal to 0, but that's not exactly going to work. So we want to move one forward. Maybe we don't. If we could get past this one case, I feel confident that we could solve it. Maybe if height sub left is less than height sub right, so we do one of those things where we don't want each other to pass while left is less than right. Right, if height sub left is less than height sub right, which it is, right, what do we want to do? We want to calculate rainwater, but there's nothing to calculate, right? So maybe, right, we'll try and calculate anyway, and during this calculation we'll move it forward. So maybe we'll save our current indice. So say, current equals right, current equals left, and we want to move forward, right? We want to move forward while height sub left, right, until we find a height sub left that is greater than or equal to current, right? And while height sub left is greater than or equal to current, right, we do left plus equal 1, right? We do left plus equal 1, but since we're iterating for, we might as well calculate the water for it, right? So we'll declare water. We could do water plus equal maybe height, the current, or maybe the minimum of both. Height is greater than or equal to current. So height is greater than or equal to current, so height sub left would be 0, while height sub left is greater than or equal to current, which would be 0. We'd go forward once, we want to calculate it, but 0 minus 0, you would do plus equal height sub left, or I guess height sub current, which would be where we started, minus height sub left, which would be 0, right? Then we'd go further again, right, to 1, and it'd be like, while height sub left is greater than or equal to current, which would be 1, right? So this is actually not maybe this is not the way we want to go. Maybe we want to go with less than or equal to, because we'd never ever actually stop. So a height sub left is less than or equal to current. We go forward, calculate the water, we wouldn't add anything. And then left would be here. Okay. So we would stop there. So left would be 1 and right would still be 9 or 11, I think. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Yeah, so 11. So we'd have 1, and then we'd have else, right? So this would be in the case where they're both basically the same, because one would equal height sub left and height sub right would be the same. So we'd err on the right hand side now. So we take current equals right, right? And so we want to go while height sub right should be 1 is less than or equal to sub right is less than or equal to height sub right is less than or equal to height sub right, which would be 1. Want to go while 1 would be less than or equal to 1, which means we wouldn't go further at all, which doesn't make much sense. So maybe we want, in both of these cases, what if we change the algorithm to actually do a 1 step forward progress step, so that we don't have to worry about this case where we can't do anything. So we'd restart, we'd have 0 and index 10, right? Height sub 0 is less than 1, right? So we'd want to go this way first. So current would equal left plus 1, which would be 1. So we want to go while height, oh no, not, so maybe we do current equals left, but we do left plus equals 1 just to get it started off. So we'd go to 1 here and we'd say, well, height sub left, which is 0 less than or equal to 1. 0 is less than or equal to 1. So water plus equals height sub 0 minus height sub left, which would be 0 minus 1, which would be a negative value. So it's not what we want. Maybe we only add when it's positive. We only add when it's positive. Height. Well, height sub left. There's something confusing about this. Something very confusing about this. Well, height sub left, or something I'm not grasping. Height sub left have to be less than or equal to current. If height sub left is less than or equal to current, that means that index sub 1 or index sub 0 would have to be, or index sub 1, which 1 would have to be less than or equal to 0, which it isn't. So left would equal 1. We'd stop there. Left equals 1, right equals index 10. And so we want to do if height sub left is less than height sub right. Well, 1 is not less than 1, so we go current equals right minus 1. So right would actually be at 9. I mean current, yeah, right would be at 9. So we actually want this to mimic the above. We do right minus equal 1. So we'd have right would be at current would start at 10, right? But right would technically be here, which would be a height of 2. So is 2 less than or equal to current, to height current? No. but it's still got to move forward once. And so I think we could do water. We can copy it for this one just for now, right, minus equal 1. So that wouldn't run. So we'd have right would now be equal to 9. So we have 1 and index 9. 0, 1, 2, 3, 4, 5, 6, 7, 8. No, we have, wait, what? 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. I'm pretty sure this would be 10. I don't know why I put it to 9. Zero, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So 11, that means we started at 10. Move forward once, it would be 9. So 0, 1, 2, 3, 4, 5, 6, 7. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Oh, I think I'm confusing myself. There's 12 indices. So we actually started 11. This would be 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 12. Right, so there's 12. We started 11. We have 10. So is 1 less than 2? It is. So we'd say current equals left, which would be this index right here. Left plus equals 1, so we'd be here. And so we'd have while height sub left is less than, which it is, 0 is less than 1. Water plus equals height sub current, which would be 1, minus height sub left, which would be 0. So we'd add 1 to water. And left would go forward again. Left would now be 3, 0, 1, 2, 3, right? And so while height left, which is 2, is less than or equal to current, is not less than or equal to current, so we'd stop. Right, we go to the next iteration to check if 2 is less than 2. It is not, so we go into else. Current equals right. So current equals right, which would be 10. Right minus equal 1, so right would actually be 9 now. So we'd be here, and we'd say while height sub right, which is 1, is less than. So height sub right is equal to 1. Is less than or equal to height sub current, which is 2. It is, so we do water plus equal height sub current, which is 2, minus height sub left, which is 1, which gives us 1. Then we do right minus equal, which gives us 8. And then we check if 2 is less than or equal to 2. So maybe we don't want the equals. So there's only 2 minutes left, so I'm just going to implement it. Left equals 0, left right equals height dot length minus 1. Have water equals 0, while left is less than right. We would do if height sub left, right, is less than height sub right. We would do our special case. We would do const current equals left, left plus equal 1. And we would do while height sub left. And we're just going to say less than. But we have to do, actually no, we can do less than. Height sub left is less than height sub current. Then we'll do water plus equal height sub current. So we'll just create potential water equals height sub current minus height sub left. And if potential water is greater than 0, then we'll add potential water to water, otherwise we'll do 0. And we can kind of just do something very similar over here. We'll do const current equals right minus equal 1, while height sub right is less than height sub current. And then we'll copy these two lines up here. Now uncomment this left plus equals 1. And uncomment this one. Height sub current. And I think we have to return water. And I'll delete all the pseudocode. And let's see how this looks. So we're off by 1. Very similar problem that we had yesterday. We're off by 1. But if we shorten our answer, just like yesterday, I'm pretty sure we get the right answer. There's a case we're missing. That is unfortunate. There's a case that we're missing. There's a case that we're missing that is a little frustrating. So I'm going to slowly add back the numbers and figure out which one introduces the error. So it looks like right here, 1, 0, 1. Where is that? 1, 0, 1. My output is 1. Current equals right minus equal 1. It's right here with 1, 0, 1. So let's just run the code. Honestly, we'll have 0 and let me see if I can make it smaller and still create that error. Let's just say we have 1, 0, 1. Okay, so I say the problem, it's 1, 0, 1. What is going on here? So we have left equals 0 and right equals length of 3 minus 1, which is 2. Okay, left is less than right because 0 is less than 2. Is 1 less than 1? No, so we're going to go right. Const current equals right. So we're going to save index 2, right minus 1 equals index 1. So while height sub right, which is 0, is less than height sub current, so we should have a rainwater value there. Height sub right is at index 1, which would be 0. 0 is less than height sub current, which is 1. Potential water equals height sub current, which is 0 minus height sub left. Height sub current is 1. 1 minus 0. Oh. I see. 1 minus 0. No. 1 minus 0 would be 1. So water plus equals 1 is greater than 0. It should be, yeah, we should get a value for that. Height sub current has a value of 1 and left has a value of 0. 1 minus 0. 1 minus 0 is 1. So water should be plus equals 1. I'm just gonna print. So that checks out. So I'm wondering if it's this part. While height sub right would be 0. 0 is less than 1. So that checks out too. So I'm gonna do height sub current and also height sub left to make sure that we didn't, maybe we messed up when we ran the code in our head. Okay, so height sub current. So we're actually getting 1, 1. So that's even stranger. So current is the current indice that we're at, that we want to save. So height sub right equals 1, right minus equals 1. While height sub right yeah, something's fishy here. We're getting, so current, we're getting 1 and 1 for both. So I'm just gonna print the indices, because if we have current equals right minus equal 1, these should be two different values. We should be looking for a value of 1 and 2 here. So potential water is 0. Current actually equals index 2. Oh my God. We're using left instead of right. How did I make that mistake? Let's try this again. Oh man, that is so cringe. We had it going the first time. I wonder, actually, let me go all the way back. I wonder if my pseudocode was correct. No, my pseudocode was wrong. So that's a really important thing to note. When the pseudocode is wrong, I also follow the pseudocode. Well, that's the point, right? When I run the pseudocode in my head, it should be correct. So when the pseudocode is wrong, then the code I write is basically wrong. That's why when I write the pseudocode, I have to make sure that the code actually produces the intended result. That is very, 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 very interesting. Let's read some solutions. Do as directed in question. For each element in the array, we find the maximum level of water it can trap after the rain, which is equal to the minimum of maximum height of bars on both sides minus its own height. Initialize answer equals 0. Iterate from the array from left to right. Initialize left max equals 0 and right max equals 0. Iterate from the current element to the beginning of the array. Left max equals the max of left max, or height sub j. In this case, we get 0. Iterate from the current element to the end of the array. Right max equals max, which is 0, or height sub j. Height max for this potential problem would be 3, so we'd have 0 and 3. Then we'd add the min of 0 minus height sub I to the answer. So what are they doing here when they're doing this? We take an indice, iterate from the current element to the beginning of the array. Then we find another element, or element to the end of the array. So we'd be here. The max element we've seen so far is 2. And they're trying to go from 2 up until right max, which is 3. And then we add the min of left max, which would be 2. So we take the smallest which would be 2 minus height sub I to ands. This brute force one is strange. In brute force, we iterate over the left and right parts again and again, just to find the highest bar size up to that index. This could be stored. Find max height up to the given point from left end. Find the maximum height of bar from the left end up to an index I. Find the maximum height of bar from the right end up to an index I. Iterate over the height and update answer. Yeah, this is the one that makes the most sense to me. So as an approach to, instead of computing the left and right parts separately, we may think of some way to do it in one iteration. From the figure in dynamic programming approach, notice that as long as right max sub I is greater than left max sub I, element 0 to 6, the water trap depends on the left max, and similar is the case when left underscore max sub I is greater than right max. So we can say that if there is a left max from the figure in dynamic programming approach, notice that as long as right max sub I is greater than left max sub I, the water trap depends on the left max, no, left min. Left max sub I is greater than right max sub I. The water trap depends on the right min. So we can say that there is a larger bar at one end, say right. We are sure that the water trap would be dependent on the height of the bar in the current direction from left to right. As soon as we find the bar at the other end, right, smaller, we start iterating in opposite direction. Once between left max and right max during the iteration, now we can do it in one iteration using 2 pointers, switching between the two. So make sure I'm understanding this. As in approach 2, instead of computing the left and right parts separately, we may think of some way to do it in one iteration. From the figure in dynamic programming approach, notice that as long as right max sub I is greater than left max sub I, right max sub I is greater than left max sub I. 0, 1, 2, 3, 4, 5, 6. Maybe they meet up here. The water trap depends upon the left max. I see what they're saying. It does depend on the left max. The water trap depends on left, and similar is the case when left max sub I is greater than right max. When left max sub I is greater than right max, the water trap depends on the right max. If there is a larger bar at one end, say right, that if there is a larger bar at one end, say right, we are sure that the water trap would be dependent on the height of the bar in the current direction from left to right. And as soon as we find the bar at the other end, right, smaller, we start iterating in the opposite direction. Right, that's what we're doing. The opposite direction. We must maintain left max and right max during the iteration. Now we can do it in one iteration using 2 pointers switching between the two. So left is 0, right pointer to size -1, while left is less than right. If left is smaller than height sub right, then we know that the water trap depends on the right max. So we can iterate until we if height sub left is greater than left max. So we're using a different approach here actually slightly. So you're saying left is 0, right is here. Left max equals 0, right max equals 0. Since 0 is less than 1, height sub left is greater than or equal to left max, update left max, else add left max. So let me see the difference between them. I'm doing left equals 0, right equals height dot length -1, left max equals 0, right? So they're keeping a left max and a right max. And they're just keeping an answer variable. While left is left and right, we're doing the same thing. If height sub left is less than height sub right, okay, I'm with them there. Height sub left, I don't know what this C++ greater than equal operator is. Left sub max, if left max, yeah, the way they, I don't know why they wrote it this way, because it's like impossible to follow. I don't know what this greater than equal operator does. There's also like a weird, this is the ternary, but it looks like left max equals height sub left. They're literally putting expressions in the ternary. Answer plus, these are expressions. This is strange. I think this actually hurts readability. I don't know if there's a max needed here. Mine's is without a max. The intuition, what am I aiming for behind mine? What I'm aiming for is, the way mine is working is that once you find that there are two, there's a basic premise, right? If you have two chances to choose from a side to go from, whichever side is larger than the other side, so for example, we have this one here, we know that the height of the water is going to be bounded by whenever we have the smallest one, right, we know that the height of the water is going to be bounded by the height of the lowest point. So if we have 2 here, right, we know that the best we can ever really do is 2 blocks. So we just keep going until we find that block, and then as we're going through, we add those water blocks, subtracting them in height. The reason we keep switching back and forth is because we have to make sure that this only works if we know that we're starting from a low point going to a high point. We start from a high point, it gets confusing. I guess that's why they're using maxes. So if I had to compress mine, it's basically that the height of the water is bounded by the minimum height between the bounds. So if the bound is 2 and 3, the height of the water is bounded by the minimum of the two, which is 2 water heights. So we'll have to do this one again tomorrow just to make sure it makes sense. I'm wondering if I can remove this part and just do potential water. But I don't think we can. Oh, I guess we can. Okay, so you still can. So I don't know why I had that there. In what case would you have a negative number being added? You'd have 2, and then a larger one, but this while loop only ever runs while it's less, while height sub right is less than current. So we're pretty much we're pretty much guaranteeing that the answer will never be less than 0. So that is good. We'll set another timer. We'll do a random weighted problem. Number of 1 bits. So write a function that takes an unsigned integer and returns a number of 1 bits it has, also known as the Hamming weight. Okay, so we're counting the number of 1 bits an unsigned or positive only integer can have. Note that in some languages such as Java, there is no unsigned integer type. In this case, the input will be given as a signed integer type. It should not affect your implementation. Integer's internal binary representation is the same, whether it is signed or unsigned. In Java, the compiler represents the signed integers. Make this smaller. Using 2's complement notation, therefore, in example 3, the input represents the signed integer -3. So we're counting the number of 1 bits in the number. We have the number 32-bit positive only integer. Number of 3's here is going to be 3. Number of 1's in this number is going to be 1. So there are 2 ways to go about this. I think the safe way is with bit shifting. So what we could do is we could do 32 operations over n. We'll keep track of a variable called ham, right? And we'll do ham plus equal n and 1. Then here we'll just bit shift n. We'll do 1 bit shift n right. Then we should be able to return ham. So let's check if this works. So we'd have n equals 1, 0, 1, 1. We do ham plus equal n and 1. So massing n and 1, we will get 1. So we'll add 1, and we'll bit shift n1 to the right. So then it would be 1, 0, 1. Then we do another 1, do ham plus equal n and 1. So we'd have 2. Bit shift n1 to the right, so we'd have 1, 0. We do ham plus equal n and 1. That would be 0 because 0 and 1 is 0. And then we shifted 1 to the right, and then we have 1. So we can guarantee we can do this in 32 operations if we just do a for loop. Do I plus plus. We do ham plus equal n and 1, and then we'll bit shift n to the right 1. So delete the pseudo. I'll double check to make sure my pseudocode matches. My actual code matches the pseudocode. And so I forgot a semicolon. But this does work. I also think there's another solution. I think there's another solution you can use that is actually uses more integer special bit shifting. I think we know that the least significant number for a number, right? If we have a number like this would be 1, 2, 4, 8. So this would be 9. If we could do this in n operations, where n is the number of ones actually in the number, which is technically constant time, since our original operation is 32 operations, which is constant time. Guarantee that for any 32-bit unsigned integer, you can do it in 32 operations. So in this one, we can do it due to the number of operations in number of ones in the number. I think this is because the least significant bit in a number is represented by that number minus 1. Take n, do 8, 9 minus 1, we actually get 8, and 8 is represented by 1, 0, 0. So what we can do is keep setting n equal to the and. So now I have 1000, right? We want to move n to 1000 now and keep repeating this operation over and over again. So we'll take the mask of n and 8, and we should get the and of would give us 8. So let's try this with a larger number like 18. So we have 1, 2, 4, 8, 16. 16 would be here. Let's just say we had 17. Let's just say we had 18. So if this is 18, right? We do 16, right? So 17 would be 18 minus 1 would be 17. Would this remove this 1 right here? I think so. But what is 17 represented by? Yeah, there's another version of this with n and n minus 1. Struggling to recall it. We can do while copy equals n. We'll do while copy does not equal 0. We'll do the ham plus equal 1, and then we'll set n equal to the and of n minus 1. And we don't want to use n because we just changed it to copy. This works, but the intuition is messing me up. If we have 18, 18 is represented by, we have 0, 1, 0. No, we have 1, 2, 4, 8, 16. 16 represented here, and we have 1 here to represent the 2. So we have 18. 17 will be represented by 1, 0, 0, 0. 1 like this, so we'd be removing a 1 I see. I think it's the and actually that does the magic here, because when we do and, we'd get 1, 0, 0, 0, 0, 0, 0. So our output would be which would end up removing the actual least significant bit. We would have 16 minus 1 would be 15. 15 is represented by 8, 4, 8, 4, 2, 1. And so this would actually turn to, I see, it would actually turn to 0 because the end of both of these. That's very interesting. So we do the a little fast. Instead of checking every bit of the number, we repeatedly flip the least significant one bit of the number to 0. Repeatedly flip the least significant one bit of the number to 0 and add 1 to the sum. As soon as the number becomes 0, we know it does not have any more 1 bits. We return the sum. The key idea here is to realize that for any number n, doing a bitwise, for any number n, doing a bitwise AND of n and n minus 1 flips the least significant 1 bit in n to 0. So doing a bitwise AND of 1001 and 1000 removes the least significant bit. So the binary rotations of n and n minus 1. So we have n 11011, n minus 1 0. We take the AND. I see up until the major number would stay the same. In the binary representation, least significant 1 bit in n always corresponds. In binary rep, the least significant 1 bit in n always corresponds to a 0 bit in n minus 1. So the least significant 1 bit always corresponds to a 0 bit in n minus 1. That is very interesting. Therefore, ANDing the two numbers n and n minus 1 always flips the least significant 1 bit in n to 0 and keeps all the other bits the same. Fancy stuff. Fancy stuff. That looks good. Let's try a problem from the grind 75. Let's try TwoSum. God, I'm drinking water like a caveman. Given an array of integers, so you have an array of, we have a function TwoSum, we have an array of numbers, we have a number returning an array of numbers. Given an array of integers nums and an integer target, which is 9, return the indices of the two numbers such that they add up the target. You may assume that each input would have exactly one solution. You may not use the same element twice. And return the answer in any order. Oh, that's cool. So two numbers that add up to 9 are 0 and 1. So I think we can, only one valid answer exists. Can you come up with an algorithm that is less than n squared time complexity? Well, I think if we imagine the problem like this, we sort the numbers, and then if we sort the numbers from 3 to 4, it become 2, 3, 4. So I think if we sort the numbers, we get from 3 to 4. Let's just say our target is 6, we could iterate, thinking of a two-pointer type of solution where we have one pointer at the front, one pointer at the end. And since it's sorted, if our sum is greater than the number, then we can move the right pointer down, and if it's less than the number, we can move the left pointer up. So iterate while left less than right, and you could say if num left less than num right. Oh, we have to calculate the sum first, right? Calc sum. If we calc the sum, we want to say if sum is greater than target, right, then we want to do right minus equal 1. So if we do right minus equal 1, that would put our left at 3. If sum is greater than target, so actually 4 and 2, our sum would actually be correct. So we have another case here where if sum equals target, we'll just return the tuple of left and right. Else if sum is, so we need another, let's just say our target is 5. So we get 6, and so our sum is greater than target. We do right minus equal 1. Go to the next iteration, 2 plus 3 would equal target, and we would return that tuple. So let's just say we have a tougher solution like 2, 7, 11, and 5. If we sort them, we have 2, 7, 11, 5, and our target is 9. We do 15 plus 2 equals 17. So 17 would be greater than target. So we do right minus 1. We do 11 plus 2, 14 would be 13. 13 would be greater than target, so we do right minus 1. Okay. Let's say our numbers are larger. So it looks like this one still works. Final iteration, the sum would be 2 plus 7, we'd return the tuple. Let's just say our target is 27, right? So let's just say we did 15 and 2. Since 15 and 2 is less than the number, we want to do else left plus equal 1. If we do left plus equal 1, we'll have 2. We'll have index 0 will now go to index 1. So 7 plus 15 will be 22, which will still be less than 27. Then we'll get to 11, and then we can return that. I think the intuition behind this problem is that since it's sorted, if our number is too small, I think the intuition behind this problem is that 2, 7, 11, 15, intuition is that since they're sorted, if we're at the right hand side, we're at the largest we can possibly be, and if we're at the left hand side, we're at the smallest we can possibly be. If we're at the largest we can possibly be and we're smaller than the number, then the best we can do is move the left side up. If we're at the smallest we can possibly be and we're too big for the number, the best we can do is move our largest down 1. So I think this makes sense. They don't say to hand, they said that each input would have exactly one solution, and you can determine the answer in any order, but we'll just return an empty array when we can't figure it out. So to sort it, we'll do nums.sort, and we'll sort it in place. We do while A minus B. We do while left is less than right. We'll calculate the sum. Sum is going to be num sub left plus num sub right, and we'll say if sum equals target. Then we'll just uncomment this line. We return the tuple that the two indices that give us the sum. Otherwise, we'll uncomment this line. just uncomment the remaining lines. So remove the pseudocode. This looks good, so we'll run it to try it. So syntax error, while left is less than right, we don't even have a left and right. Left would be equal to 0, and right would be equal to nums.length minus 1. Insert the numbers in place. Sum would be equal to num sub left plus num sub right. Sum equals target, return left. Tuple of left and right. Otherwise slide down right, otherwise slide left forward. Nums. Okay, so our target is 6, and in this case, we're failing. So 0 goes to 2, the sum is left plus right. So 3 plus 4 would be 7. That's where the largest we can be, and then sum is greater than target. We would do our output is 0. Output is 0 and 2. So let's run it again. We have 3, 2, 4. We sorted, we get 2, 3, 4. On the first iteration, we do num sub left would be 0, 1. I see. If we sort it, then we can't return the indices that give us the correct answer. So give us n log n bound. But we could also just go and find the number that we're talking about. Only one answer exists. Okay, if the sum equals the target, might make more sense to copy it. Copy the array, then we can just search for the indices in reverse that gave us the answer. That would be less. This would still be a good time. So those are at least one answer, so we don't have to return this array. Sum equals target, then we will break, and then so we'll search for the left index. We'll say left idx equals 0, and we'll search over nums, the entirety of nums. We'll say if copy sub left equals nums sub I. Left idx equals I, and we'll break. And we'll do the same write IDX. But for write IDX, we'll iterate in reverse. This one, well, I is greater than or equal to 0. Copy sub. Write equals num sub I. That means we found the index we were looking for. So write index equals I. We can also, no, yeah. I, and we could return what index, right index. The answer is still good. This one should be resilient to index changes. So since we copied the array, we just want to use copy instead of nums. You're going to find the indices as to where was num sub I. So this works, but it's a little sloppy since you have to. We keep a copy of the array since we have to sort it, because the indices we have to return the indices that actually sum to 2 and not the actual numbers that sum to 2. So we have to go searching for the indexes again. I can't see a solution where we don't have to go and find the original indices again. Follow, yes. So we can do better than n squared. This is actually bounded by the time it takes to sort the list, which would be log of n log n. And we have to search over n again, so it's n log n times 3n. We drop the constants though, so it's just n log n. Is there a way to remove these two searches? Is there a way to remove the two searches of these two indices? So we're citing it, the algorithm is dependent on sliding it up and down, and that requires a sorted array. To do it in an unsorted array, we could do it in linear time with maybe a map. Maybe we could do it in linear time with a map. That way we would know instantaneously, since there's only one answer. Actually, if we create a map, iterate over nums, on each iteration, not a map, a set, iterate over nums, each point in the set, check if target minus num sub I in set. Oh, that's why we need the map, because we need to know the indice in set. If so, return the tuple. Otherwise, add to map. So how would this work? So we create the map, and we'd have 3 to be index 1, and the map would store a number to an index. So 3 would be set to 0, 2 would be set to 1, 4 would be set to 2. We iterate over, so we iterate over nums. Now we're at 3. Check if target, which would be 6 minus 3 in the set. It's not, so we'd add 3 going to index 0. Then we'd go to n in the set. We'd go 2 in the set. We'd go to the next number in the iteration, which would be 2. We would check if 6 minus 2, which is 4, is in the set. It's not, so we add 2 to the map. When we get to 4, we would check if 4 minus 2 is 6, which is the target, minus 4 in the map. So it's 2 in the map. Yes. What's the index? Then we return the tuple of both. So it looks like this works. Const map equals the map of number to number. We could iterate for const num of nums. And we'll handle the else case first, just because it's a little easier to handle the if. So we do math.set. And we actually want the number as well. Nums.entries. We would do map the number to the index. We check if map.has target minus number. Right, so we want to return this tuple, so we'd return map.get target minus number, which would be the first index, and then we would also return it with this index. So that works as well. I think that's good enough for 2 solutions. This one is linear time. Linear time with linear space, whereas the other one is n log n time with constant space. Brute force is pick an element, iterate over every element twice, thus checking if they add up to target at the n by n time complexity. Or n to the n. 2-pass hash table. To improve our one-time complexity, we need a more efficient way to check if the complement exists in the array. If the complement exists, we need to get its index. It's the best way to maintain a mapping of each element in the array to its index. A hash table can reduce the lookup from linear time to constant time, creating space for speed. A hash table is well suited for this purpose because it supports fast lookup in near constant time. Say near because if a collision occurred, the lookup could degenerate to linear time. However, lookup in a hash table should be amortized to constant time, as long as the hash function was chosen carefully. Simple implementation uses 2 iterations. First iteration, we had each element's value as a key and its index as a value to the hash table. Then in the second iteration, we check if each element's complement targets minus nums 1 is in the hash table. If it does not exist, we return the current element's index and its complement's index. Be aware that the complement must not be nums by itself. So we prevent that by only adding the number to the map if it doesn't exist. So it looks like we did the 1-pass hash version. So looks good. We can add that. This one looks good. I'll do another weighted problem. need for this timer since there's only 15 minutes left. So we have function num islands, and we have a grid, which is a multi-dimensional array. We have to return a number. Given an m by n 2D binary grid, which represents a map of ones, land and zeros, water, return a number of islands. Island is surrounded by water and is formed by connecting adjacent lands horizontally or vertically. May assume all 4 edges of the grid are surrounded by water. So this is our grid, that's m by n. 1 is land, 0 is water. Return the number of islands. Island is surrounded by water, is formed by connecting adjacent lands horizontally or vertically. So this is one island because all these pockets of ones are connected horizontally by 1, 1, which means one island. There's 3 islands here because there are 3 pockets of ones, but none of them are connected. They're all connected diagonally, but an island only counts if it's connected horizontally or vertically. So therefore there are 3 separate islands. M equals grid length, n equals grid sub I dot length. There's always at least 1 row and 1 column. Grid I sub j is equal to 0, 1, so we don't have to worry about any malicious inputs. So what we could do is visualize this grid as a graph, and if we visualize it as, actually the way we could visualize is that we have this grid. We know that once we find a 1, we have confirmation of an island. So a very naive implementation looks like islands, iterate over grid rows, iterate over grid columns, right? And if we count all the 1s, this would give us the wrong answer. But instead we could use the 1s to trigger a function which will clean up all connected islands. So if we do that, we could say if grid sub row sub call equals 1, right? Then we know that we found at least 1 island, right? And we also know that we want to call clean islands. At the end, we would return islands. So if we went like this as so far, if we could create this function clean islands, that would, once we find this 1, we'd increment islands by 1. It would clear out all the connecting 1s. Then we could keep iterating. So it would be m by n time complexity until we reach the next island. It would clear out this 1, and then we'd keep going, and find 1 more island, making island plus equal 3, clearing out the remaining 1s. So this clean island function would take a grid, take the grid as it is, and a row and a column. These would just be numbers. And it wouldn't return anything. And then from here, we would just have to validate that a cell is valid, basically, right? And it says you may assume all 4 edges of the grid are all surrounded by water. If that's the case, then when we check for each cell, we're going to check the up, left, right, and bottom, right, and clear out those values. If we find another 1, we're actually going to call clean island again, right, to keep cleaning it out. That being the case, we need a way to validate a cell, so we'll have function cell invalid, and we'll do string, we'll do row number, call number, and return a boolean, and a cell will be invalid if row is less than 0, or column is less than 0, or row is greater than grid.length, or column is greater than grid sub row, dot length, or since we validated that both at this point in the or we validated that row and column are both valid numbers. We want to make sure that grid sub row sub column does not equal a 0 node, right? Which would mean that it's an island, because if it's an island, we don't want to trigger clean island. So here we can implement islands equals 0. We'll iterate over the grid's rows. So I will do row equals 0. Row is less than grid dot length. Row plus plus. Duplicate this line and we'll place it right below the pseudocode. Move it up. Change a row equal to column. And call, right? Column length is going to depend on the row that we're in. It's going to be grid sub row dot length. We call plus plus, and we want to assure that grid sub row sub call equals a 1, which means that we want to kick off the code that we wrote, and we'll call clean islands with grid row and call. So clean island is going to be recursive, and it's going to operate similar to a depth first search, except the 4 nodes that will, or the depth first search, the 4 nodes that we'll visit will actually be up, left, right, and bottom, because we want to make sure that validate that the connections, or clean up any nearby islands that we can continue iterating through without having to worry about running into duplicate ones. So we call clean island. We want to make sure that if the cell is invalid, that we just return, right? If the cell is invalid, there's no point in running the code, so we just return void. Not getting any highlighting, so I'm thinking I'm missing something. Row is less than 0, or call is less than 0, or row is greater than grid length, or call is greater than grid sub row dot length. Grid sub row sub call equals 0. So it seems to be good. I'm not really seeing what the problem was. So if the cell's invalid, we don't want to waste any time, right? But if the cell's valid, right, that means that we want to set the current place we're at to a 0 node and invalidate it, right? But then we also have to check up, right, left, bottom, and behind us. So that's going to look like 4 calls of if the cell is not invalid, right, with grid row sub call. For this one, we'll check above us first with call plus 1. If the cell is not invalid, then call clean island for that grid and row column combo. Duplicate this 3 times. We want to check above us, below us, behind us, and we also want to check to the right of us, which should be plus 1. Okay. So I think this should work. On one car 51, a comma was expected. That's what the problem was. Function was called clean islands. Maximum call stack exceeded. So our maximum call stack is exceeded. So we might be going too deep. We call it clean island. Check if the cell's invalid. The cell isn't invalid, then we want to clean the island. Might be simpler, back to check validity if we just remove this part about it being equal to 0. Still running out of stack space. So it's possible cells invalid, grid, row, column. So if we check this out, we would go to 1, then we would check above us, that would be out of bounds, so this cell would be invalid. We check behind, down, so we go down, then we check above us, basically we don't want to run clean island unless the equals 1. We could nullish coalesce this whole thing. We could say if grid equals 1, then call clean island. I forgot to do the. So this version works. This version is a simpler version where I just nullishly coalesce if check if the value equals 1 before I do it. But I think what I was doing above is even if the cell is invalid if it equals, we want to skip calling this function for cells when they equal 0. So basically we're doing a root node that triggers a depth first search. If the node contains 1, then it's a root node that triggers a depth first search. During depth first search, every visited node should be set 0 to mark as visited node. Count the number of root nodes that trigger DFS. This number would be the number of islands in each DFS, starting at some root identifies an island. So we did the same thing that we did. Interesting. Looks good. Looks good.